Jonathan, it just looks like you're on mute. So
Failed facilitation number 1. There we go. Hopefully that's coming through nice and clear. Thanks, Taru. I'd too like to extend my welcome to you all, whether you're joining us here in Australia or joining us around the world. I'm the Managing Director of Greenview Strategic Consulting. We're a boutique consulting firm specialising in market integration of wind, solar and battery generation here in the NEM. And we're based on the east coast of Australia. Our organisation is a member of ESIG and has been for several years, so I'm really pleased and honoured to be facilitating this session, adapting to increasing decentralisation. Given my background is mostly in the utility side of the energy grid, you may be asking, why am I in this facilitation seat? Well, if you've been listening to some of the previous ESIG Down Under sessions, you'll know that many of the presentations have highlighted the issues that are occurring, particularly around DR here in Australia, but also around the world, and that these challenges require significant thought and practical understanding. Here in today's session, we're going to get some of those details and go into some of those details to a level of technical understanding. That means that we're going to start to talk about these solutions, how much time we've got to start addressing some of them, and more importantly, how much it may or may not cost. So to that extent, I'd like to introduce you to our 3 high-quality speakers for today. Chris Davies joins us from AEMO, the market operator here in Australia. Elizabeth Maynard from Node Energy Services will take us through some of the technical considerations in the integration of distributed generation. And finally, we're going to hear from Hugo Klingenberg from Electronet, the TNSP or TSO here in South Australia. Before I hand over to Chris, I just wanted to remind everyone that we're going to be using Slido for Q&A and that you can use the hashtag ESIG-3A, so that's ESIG-3A for your questions, making sure you put the name of the speaker, or you can put all at the start of the message and we'll get to those at the end of the presentations. This session is being recorded, as Taru said, and will be available on YouTube in the next day or so. So in conjunction with the other items that are already online, this is going to be another rich resource for us all. Having seen the presentations, I know today is going to be a great session, but I'll also be working hard to make sure we have plenty of time for discussions, and I look forward to getting through as many of those as possible. So without further ado, I'd like to introduce Chris Davies from AEMO. And Chris is responsible for AEMO's Future Energy Systems team, whose core function is to identify and communicate emerging power system limits as the generation mix changes, including reviewing technical requirements, standards, and the technical specification of the system services. Chris has been with AEMO for 4 years, and during this time, Chris has had lead roles in addressing a number of emerging power system and regulatory challenges, including establishment of AEMO's Future Power System Security Program and the specification of new technical standards for distributed energy resources. Prior to joining AEMO, Chris worked in engineering consulting, supporting electricity and gas projects across Australia, the Philippines, Chile, and the Pacific. Chris holds a degree in photovoltaics and solar engineering from the University of New South Wales. Thanks, Chris.
Thanks, Jonathan. Can you hear me okay?
Yes.
Beautiful. Look, thanks everyone for joining us this morning in Australia and whatever time it is for you around the world. Today I'm going to be talking about AEMO's renewable integration study, which we published in April this year, and was a study looking at how we integrate increasing levels of wind and solar generation into Australia's national electricity market, or NEM. Given the sort of 10-minute time limit I've got, I thought I'd focus today's discussion on a summary of that study's findings, particularly in the area of adapting to increasing distributed generation. So just to kick off, a few fast facts about the NEM and why distributed generation is becoming of such interest for us here. We have a system of a peak demand around 35 gigawatts. And in 2019, we had an installed capacity of distributed solar PV of just over 8 gigawatts. So here we're defining distributed PV as all grid-connected solar installations that are not part of central dispatch. So that's everything from a 1 kilowatt residential rooftop PV system up to a 30 megawatt non-scheduled generator. And importantly for us, the majority of that installed distributed PV is made up of the smaller sort of residential and commercial systems, so particularly systems under 100 kilowatts. And looking ahead, so from the 8 gigawatts we've got today, our projections are that we could have over 18 gigawatts of distributed PV by 2025. So in the context of a 35 gigawatt peak system, we're talking sort of a serious proportion of generation at certain times. Next slide, please. So this graphic gives a view of what that increasing sort of capacity of distributed PV looks like operationally in terms of instantaneous penetrations in 2019 and also projections out to 2025. What we're looking at on the x-axis, we see instantaneous penetrations of distributed PV as a percentage of underlying demand, and on the y-axis, underlying demand with a different chart for each region of the NEM. Each coloured data series shows the half-hourly distribution of distributed PV penetration for a single year. So in grey, we see the 2019 actuals. In red, a projection for 2025 from the central scenario of our integrated system plan, ISP. And in orange, a projection for 2025 from the step change scenario of our ISP. And the key takeaways here really are, firstly, the increasing penetrations over time, but also the different trajectories that we're seeing for each region of the NEM. So it's not a uniform sort of whole of system growth. And particularly if you look at the top of the chart there, some extreme penetrations already in South Australia. So we've seen periods where 65% of operational demand is being met, or underlying demand, sorry, is being met by distributed PV. And Hugo, I think, will talk a little bit more about some of the South Australian challenges after me. What we did in the renewable integration study was to look at what the different challenges are that emerge in the system as we move up through these penetrations. So that included looking at challenges emerging in the distribution networks, then propagating up into transmission networks, and also for the bulk power system as a whole. Today, I'm just going to touch on some of the bulk system challenges. Next slide, please. So from a system operator's perspective, the challenges of managing increasing levels of distributed PV span a number of areas. First is the response of distributed PV to power system disturbances. So in particular, the potential contingency size we get if a large volume of distributed PV was to disconnect as a result of a system event. Next is the erosion of operational demand during the middle of the day, which creates a number of challenges of its own. So firstly, maintaining sufficient level of operational demand to support the minimum loading levels of the minimum number of synchronous generators that we need to have online for system services that can't be served by distributed PV. So things like system strength, inertia, and some frequency control services. Next is having enough stable load available for emergency under frequency load shedding for those schemes to be able to work properly. And lastly, increasing challenges in the management of transmission network voltages. And I think Hugo might also touch a little bit on that. We also see challenges associated with the variable characteristics of distributed PV. So firstly, there's just the management of the increasing daily ramp requirements as solar comes online in the morning, goes away in the evening, and sort of accounting for that in the dispatch of large generation. And then as a further complication, sort of how you manage sudden cloud movements over metropolitan areas that can significantly exacerbate the rate of those ramps that need to be covered by your dispatchable fleet. The last area then is the fact that distributed PV is a source of generation at the moment that can't be actively managed or curtailed. So this, for us as system operator, reduces the operational levers available for helping us keep supply and demand balance during normal operation. And it also raises questions about how we maintain sufficient operational levers to rapidly rebalance the system during some extreme abnormal system conditions. So here we're thinking about sort of high solar, low underlying demand days on a spring weekend combined with an interconnector outage, would leave us really exposed if we were then to experience a contingency event on the system. I think Hugo and Elizabeth will touch a little bit more on some of these challenges. Next slide, please. So managing this increasing decentralisation in generation technologies, we really add a whole layer of complexity to how we have to think about planning and operating the electricity system. And as a result of that, I guess that transition means we have to look at a large combination of solutions to effectively cover all the system requirements we need under all different system conditions. Firstly, we need appropriate market enablers that give the right signals to optimize the use of distributed generation with load and with storage. So trying to help balance those as best you can and soak up that excess generation during the middle of the day. Secondly, we need adequate data and information to predict system performance and also to optimize system operation across the distribution, transmission and bulk power system. And then we also need a suite of technical enablers to complement that. And that we can look at in terms of device level enablers on distributed PV systems themselves. So that includes sort of standards, the ability to actively manage outputs, or for someone to be able to do that, and some kind of emergency curtailment functionality for those extreme abnormal conditions. We then look at load and storage solutions. So as I said, essentially introducing sources of demand to soak up excess distributed PV generation during the day. And then also system management solutions. So this comes in the form of procurement of reserves to better manage risks associated with mass distributed PV disconnection, and also considering sort of operating the system in a more conservative manner to reduce or eliminate the chance of getting into high risk or inoperable system conditions. And lastly then, network development solutions. So these relate to enabling better sharing of distributed PV between regions and also reducing the likelihood of regions islanding from one another. Next slide, please. So that's a rapid fire sort of summary of some of the key findings from the renewable integration study on distributed generation, and 10 minutes is a tricky time to delve right down into the weeds. So I think we'll use Q&A to really sort of be guided by you guys in terms of specific questions you like to probe into, but also anyone that's really interested in delving deeper into these questions, there's a host of great resources that present in detail our recent work and analysis in this area. So in particular, the Renewable Integration Study Stage 1 report and its Appendix A report, which specifically focused on integrating distributed PV. We also produced a webinar sort of unpacking those findings in a lot more detail. And then quite a lot of common questions we got through the early stakeholder engagement when we released the study. So we've also put out a frequently asked questions paper just to try and respond to some of those. And then also we'll soon be publishing a stakeholder consultation paper in response to the written submissions we received on that report. So that also delves a bit deeper into some of the questions people have had on the distributed PV integration, and all those are available on our website. There's also 3 AEMO publications that include more recent analysis that we've done in this area since April. The links are there in the slide pack, so when this comes around, you'll be able to dive into those. And some of that work I'd point out was presented by my colleague Jenny RIS in session 2B last week. So that one's available, I think, already on the ESIG website for people to take a look at. That's enough from me. I look forward to taking questions in the second half of the session, and just thanks again for everyone for dialing in and joining us.
Great, thank you, Chris. And I particularly like the note that you had in there about improving visibility and predictability around this type of generation and load. It's, to enable that optimization, really important. Thanks again. I'd like to now introduce Elizabeth, and she's going to come and present some of the technical considerations in the integration of distribution generation. Elizabeth is an experienced team leader and power systems professional with over 15 years experience in the grid connection of renewable energy projects. She's worked across a range of roles in the industry, including technical leadership roles at leading consultancy Lloyd's Register Synergy, and recently is the principal at Node Energy Services, supporting the delivery of generator connections in them. Prior to that, she held key technical roles at AEMO, where she led AEMO's network data work team, responsible for ensuring power system data integrity for internal and external stakeholders. Thanks very much, Elizabeth.
Thank you, Jonathan. And thanks to ESIG and AIMO, obviously, for the invitation to present today. I'll just straight into the first slide, Teru. So as we've heard from Chris's presentation, there's a lot of changes happening through the process as they sort of deal with operational challenges that are bringing across influx of generation that you're seeing in the distribution level. And certainly, as we look at the ecosystem in itself, there's various technical considerations that the various parties within Matrix are sort of looking at as we try to transition and integrate a whole bunch of projects that are coming into the distribution level, both within the LV side of things, where the consumers are sort of installing rooftop PVs, as well as some of the work as consultants do in supporting some of the generation projects that are trying to connect to the distribution system. So from that perspective, certainly some of the stuff that we've always been considered previously as we integrated projects, such as in the connection study space, for those in the US, consultants sort of play a role where they sort of look at the connection studies on behalf of developers and work with the network service providers to ensure that well suited and optimized to ensure that they can have a good technical performance. So we've seen a bit of a change from what was done probably a decade ago, where the connection studies mainly focused on the quality of supply aspect. So would historically look at issues such as harmonics, voltage step changes, as well as fault level and thermals. But as we start to see some of those technical considerations that are happening around to sort of ensure that the operational issues that AIMO has highlighted managed, we are having to look at other avenues and other aspects that are previously not considered to ensure that as we shift towards this wider change, that whatever projects are connecting on that distribution level are also well suited to ensure that the performance of them be better optimized to work well within the system and sort of deal with some of the challenges that AIMO has highlighted. So from that perspective, I'll be providing some examples where we've seen some changes at the regulatory level, how those flow down to the distribution connection side of things. And certainly ourselves as consultants, as I said, we typically have to look at the technical aspects that were previously not a consideration for distributed generation. And we'll touch on a few others as DNSPs as well, deal with some of these issues, what they're changing, what are the solutions that they're trying to implement could have an impact on how a generator is trying to connect. We'll just jump to the next slide, Teru. So one of the big ones that we've always had to think about from a voltage perspective when connecting distributed projects to the network was the generator's voltage control strategy. So historically, again, this was all about the voltage step considerations. There's different distribution codes as some of these projects connect at the LV to medium voltage level. An example is in Victoria, where you've got to manage your step change to within 3% at the 66 level or 5% at the 22 level. So a lot of the optimization around ensuring that a distributed connected generator was ensuring to meet the quality of supply requirements was all about ensuring that we can meet voltage step and ensure that those fluctuations are kept within those limits. What we can start to see is when the DNSPs are considering all the influx of distributed PV lower their low voltage sections with the rooftops that are coming in, some of the solutions that they may look at when they're sort of dealing with their asset replacement programs may include replacing some of their older zone substations with OLTC. So the own load changes are historically used in transmission levels. You may see that they are now introduced in the zone substation, where these OLTCs, for example, in the little diagram on the left, will be used to control the bus voltage at the medium voltage level. So you've got a project that we would be looking to connect at the same sort of, as we need to ensure that whatever voltage control strategy that was historically just ensuring it's about the voltage step, we now need to ensure that it can well integrate with whatever's happening at the higher level. So the DNSP looks at replacement of that transformer, and all of a sudden they've got another voltage device that will be controlling the same bus that a project is trying to connect. So we'll have to look at some of those coordination aspects that are needed to ensure that both of these coordination strategies can work together, and that's anything from ensuring that the voltage set points are well coordinated and understanding what it is that the DNSP is going to be running that particular OLTC, and ensuring that the control strategy for the project, such as a wind farm or a solar farm, the power pack controllers, which also utilize closed loop control, which is slow acting in the same purpose that an OLTC is, can have some counter interactions. So some of the things we're looking at and thinking about as we sort of look at projects connecting on that distribution level is whether, for example, the DNSP is looking at any replacements in the coming future that may affect what needs to be designed as far as a voltage control strategy to ensure that we can meet both the quality of supply aspects, but also ensure that we're not having any negative counter interactions that may have other effects, as well as sort of pretty much affect what the DNSP is trying to achieve in terms of voltage management. But when you've got another controller that comes in there that's doing something to the opposite of what the DNSP is looking at, we ensure that those are sort of coordinated. So that's one of them that we've got having think about, as well as watching out for what's happening on the distribution level and ensuring that we understand what our DNSPs are doing with those particular projects before they connect, and ensuring that the distributions substations they're coming up with any replacements. We sort of talk to the DNSPs to ensure we understand those. Next slide, Tiru. Another one that we've currently sort of been seeing that has evolved over the past couple of years is in the disturbance right through space. So the 2019 Generator Technical Standards rule change introduced a wider voltage disturbance requirement. And what that meant is we saw a whole bunch of OEMs, which is the suppliers and original equipment manufacturers, ended up widening their voltage right through thresholds to meet these new requirements. Provided some good benefits in terms of both transmission, which is where a lot of the projects were connected at the time. And some of the benefits we've started seeing from that change is a project that, for example, connected maybe 5-10 years ago would have potentially not been able to ride through some of the faults that we see in the distribution level. So distribution level projects sometimes have to deal with long duration faults. So whereas we're talking milliseconds in the transmission, distributions can see some faults in the order of seconds. And historically, what we would have to do is do some analysis to see how these projects would go. And based on the capability at the time, some of these projects would then elect to sort of disconnect for that particular fault. So what we're seeing now, for example, left-hand side there, had a voltage range previously in the range of 1.1 and 0.9, where the manufacturer would sort of guarantee continuous uninterrupted operation for that range. And with the rule change that came into 2019, some of these manufacturers then extended their voltage range, can now operate between the 1.2 to 0.8 per unit range, and that's at the terminal level. And the bonus for us was we saw, for example, even at those low voltage levels, gone from a 0.62 second tolerance time, and now this similar project can, for example, survive a 0.15 unit fault, 1.7 seconds. So a good example of that would have been a particular fault in the distribution network, which would have seen the voltage, looking at the little curve that I've got there, drop from 1.03 to 5 seconds. A fault happens and the voltage collapses to 0.15 and remains at that level for maybe 1 second before recovering. So a project previously that would have connected at that level in that distribution network have had a protection setting that would trip it, so it would not be able to recover following that fault. But now with some of these widened voltage right through thresholds, we're seeing some of these solar farms or small wind farms that would have connected to those areas can now sort of ride through some of those long duration disturbances that have been seen previously in the distribution network. So that's a positive from the perspective of being able to sort of deal with some of the issues that Chris picked on in terms of the mass disconnection of some of these projects. So we've got an opportunity now that some of these other small projects that we'd have connected historically would have had to trip based on their capability. But with the advancements on the OEM side, some of these projects are now able to ride through some of the longer duration faults, which were previously would have previously had to trip, and have added to that whole challenge of having more and more projects sort of tripping when there's a disturbance somewhere in the network. Next one, Teru. So one other one that I think Chris has touched on quickly was the concept of the visibility and how some of these projects cannot be seen at the low voltage level, the rooftops, and how that's creating some of the barriers and challenges into sort of operating some of these areas. So what we've currently seen in the distribution network, it's not uncommon to have a lot of projects connecting onto the same sort of loop. So you've got little projects below the sub 5 to 30 megawatts. In Australia, these are classified as non-scheduled generators, and therefore they're not dispatchable, or they're not in the dispatch engine. And what that has meant is you get a whole bunch of projects which are connecting really genuinely next door to each other. They're the 5 megawatt wind farms, or two turbine wind farms, or sub 29 megawatt solar farms that are just trying to get below the threshold. And what that creates is an opportunity that a whole bunch of these projects that level of less than 30, which are then in theory non-scheduled generators, can all be connecting to the same area. That leads to this possible thermal congestion in that projects that are not actually in the NEM dispatch engine. So that has created some of the challenges that can be seen in that distribution level. But noting that AIM was under the NER 222B1 are able to sort of have a discretion to get some of these generators classified into semi-scheduled, which in Australia means that they can now be dispatched, and they'll be part of the dispatch process. That has been positive from that perspective of all of a sudden you've now got small generators that were previously not participating in the dispatch engine, and now are required to, by nature of the fact that they've all connected to the same part of the low voltage distribution network, possible impacts of having a congestion. Now they've got to then be integrated into the NEM dispatch process. And a recent rule change that we've seen, any projects that are going into the dispatch process, or any projects that are considered dispatchable, will now be required to provide primary frequency response. So that is probably a positive bonus from the perspective of having the increased visibility that AIMO wants to see from some of these projects. And now that once you get required to sort of be participating in the dispatch process, you must, under the new process, under the new mandatory frequency response rule change, must be able to provide primary frequency response. So some of the considerations from that perspective will be to ensure that some of these smaller projects, even as much as they're connecting onto that distribution level, by nature of the fact that they're going to be in an area of high congestion, hence get scheduled, get categorized as semi-scheduled, will need to be able to provide primary frequency response. So we need to ensure that we can work with these projects to ensure that they're tuned to be able to provide frequency response within the dead band of 0.015. So that has been a positive from that perspective of a bonus in terms of being able to also help distribution projects, also help with primary frequency response, which was something that was previously not considered, at least in that level. And it's obviously a new process now on the transmission level as well. But now you'll get a few of these smaller generators also contributing from that perspective. So I think I've run out of time, but yeah, that's so from the perspective of what we've seen, the main trends for us has been looking at change that, for example, the past decade, where we concentrated largely on supporting some of these projects and ensuring that they could meet, the voltage steps, harmonic fault level considerations. But now, as some of the things that are happening around are evolving, we can see that some of these distribution projects are also helping with supporting system security as we move forward.
That's great. Thank you very much, Elizabeth. That was wonderful. I think the importance you put on fault ride through is absolutely something that's critical. I know from the utility scale, certainly wind and solar fault ride through is just fundamental. So I think we heard last week in one of the ESIG presentations about 30 to 40% not riding through. So even if they do ride through, we've still got to figure out what to do with those deficits, those energy deficits as we go along. So yeah, thanks again. Appreciate it. Just a reminder to everyone just to keep those Slido questions coming, and certainly great opportunity to go through some of these technical issues that we're talking through. That brings me to our final speaker for this session, and that's going to be Hugo. Hugo's going to walk us through the impact of distributed resources on the South Australian transmission system, which is arguably one of the most impacted utility scale grids in the world when it comes to distributed energy resources. Hugo has over 20 years experience in the fields of power system planning and analysis, having led engineering teams in consulting, distribution and transmission companies. At Electronet, Hugo is responsible for the network development business unit, which performs the functions of power system planning, connection assessment and determining power system capability. So certainly a good one to have on our presentation today. Hugo is leading Electronet's response to the challenges in South Australia's transmission network and all the challenges that they're facing with changing load and generation mix. Thanks very much, Hugo.
Thanks, Jonathan. And I'm keen to provide a perspective from South Australia as a transmission network service provider here. Chris pointed out the challenges for the NEM ahead of us. Here in South Australia, we're living those right now, feel a bit like the canary in the coal mine. And I'd like to focus on sort of the three real-life impacts that are with us already, sort of minimum demand, DER shake-off, and the transmission distribution interface. Got a couple of slides, so if you can move on, just for a bit of context. So this first slide here, just want to highlight three key points. The first one is that South Australia is quite a sparsely populated state, which then effectively leads to or resulted in a weak transmission system. But that then combined with abundance of high quality renewable energy resources, leading penetration of wind and solar compared to demand, that creates these sort of challenges for us. But then more recently also just the collective action of rooftop PV to system events is causing quite significant concern for the South Australian transmission system. On the next slide, please, Taru, just provide some context of indicating the significant ratio of combined non-synchronous generation compared to demand, where the installed capacity exceeds 2,500 megawatts already, compared to an average demand of 1,400 and minimum demand less than 400 and declining quite rapidly. The fine print on this slide is what we want to focus on. On the next slide is the minimum demand figure here includes the contribution from embedded or rooftop PV. That, focusing on that on the next slide, if we can move on, is the big concern for us here in South Australia is under minimum demand conditions, that yellow area in that diagram there indicates that rooftop PV collectively is the biggest generator in the state under those conditions. That as such, you could argue is not a key concern. The concern though is the minimal visibility and more specifically the lack of control of the DER resources under those conditions leads to where we are in South Australia already, that for minimum demand conditions, we're relying on the Hayward interconnector into Victoria to export excess generation. Semi-scheduled generation is heavily constrained under those conditions. But then also more recently in a review of under-frequency load shedding, which has been relied on for decades for emergency response to restore supply and demand under critical conditions, that is becoming ineffective to the extent that AEMO is shortly going to introduce additional constraint on the Hayward interconnector to manage that. But also then between Electronet and SA Power Networks, the distribution company in South Australia, we're expanding the UFLS reach into customers that previously were deemed either too sensitive or too critical. So in a way, sort of no load is off limits anymore for under frequency load shedding. Those two green stars indicating the minimum demand there on the 13th of September is below that line already. So we've hit 379 2 weekends ago, and it's only the start of the minimum demand season. And according to projections, we expect to get to negative grid demand in 2023. So that in itself is quite a challenging prospect to think of. In terms of what you see below the line there is what is being exported into Victoria. So the challenge is really, if we move on to the next slide, is what happens if South Australia is an islanded operation. And recent work by AEMA has indicated that in South Australia we need about roughly 400 megawatts of demand to operate the island securely as an island. So what does the system operator actually have to do right now should we be in that condition? That is resorting to manual intervention, at least on two fronts. The one is AEMA system operator is bringing up non-scheduled generation and switching them off. And the other one that's being trialed by the distribution company is to basically raise the voltages on the distribution network, which is quite a simple but crude manner to raise the voltage to a level that the rooftop PV starts dropping off because the voltages are too high. Not an ideal outcome, but things we have to resort to actually manage the system. But looking forward, and South Australia is the first one here in Australia that needs to do this, is control of DER. So the South Australian government has mandated that from, I think it's end of September, all new rooftop PV needs to be controllable, but then also improving the standards of inverters. They are better equipped to ride through transmission type disturbances. So those actions will have an effect in future to limit the impact of the collective action of these rooftop PV generators, that the problem doesn't get too big and basically unmanageable into the future. Last point on this slide, just to point out, is we are in the process of trying to get an additional interconnector approved between the mid-north of South Australia connecting into New South Wales. And should that project go ahead, that would buy us collectively some time in this space. Then we would have two AC interconnectors into South Australia, which would then significantly reduce the risk of us islanding, and then sort of in a way manage the impact of rooftop PV from a system security perspective a bit better. On the next slide, I just want to point out that minimum demand, we looked more at the supply-demand energy balance challenge. However, at a system disturbance level, over the last years, we've learned that for significant transmission disturbances in the Adelaide Metro, that has led to quite a significant sympathetic shake-off of rooftop PVs, to an extent that between ourselves and AEMA, we had to take some action. So good work has been done by AEMA to come up with some DER models that are now being used to update the limits across the Hayward interconnector. But then also understanding is under daytime conditions where you are exposed to this risk of DER shake-off, that has an impact now on how much inertia is required in South Australia for secure system operation. And this graph here indicates that under nighttime conditions, we don't have that exposure. You have a certain amount of inertia or fast frequency response required. However, under daytime conditions, that requirement is significantly higher. And that's a direct consequence of managing for that risk that basically you need to cater for bigger credible contingency on the network. This then over time, the last couple of years has also indicated that we need additional emergency control schemes in South Australia. system integrity protection scheme was implemented following the System Black event in 2016, and that is now being upgraded to a wide area protection system, which really is heading to a space where we need to have fast monitoring systems available of detecting these big system events, given that they are really propagated through the distribution network. It's not only big generators or big transmission lines tripping that cause you significant events. The last slide I want to focus on is just looking at what does this mean for managing the interface between transmission and distribution. In South Australia, we've got about 40 of these connection points, and where we are 2 weekends ago, half of those were in reverse power flow, meaning that the transmission network absorbing energy coming in from the distribution network, which is completely different to the original design of a one-directional flow transmission into distribution down to the low voltage. So that creates the new challenges, which Elizabeth has covered off quite nicely, is what does that mean for voltage control and reactive power flow management at that interface? And with the proliferation of those non-scheduled generation, in our case, we get quite a number of 4.9 megawatt connections in the distribution system. That gets to a point that quite a number of our connection points are at risk of reaching transformer thermal limits in the reverse direction. So from a system planning point of view, we are working with SA Power Network is what are the fit for purpose parameters to manage that transmission distribution interface. Ideally, and we haven't settled on this yet, but ideally, can we keep it as simple as who's responsible for what type of voltage control at that connection point? Just from given that the complexity is increasing across the system, is can we come up with fit for purpose parameters to at least limit the complexity at certain points, interface points, to make things manageable going into the future. My point for conclusion is really that given the level of penetration of embedded distributed energy resources, these would be both rooftop PV at the household scale, but then also then on non-scheduled generation in the distribution network. It's imperative that going forward, we need to increase the scheduling control of that, and also the reactive response to add to managing the system. Otherwise, you get to a system where it's just becoming unwieldy or potentially very expensive to try and manage that if we don't get some control into that space. I might leave it there, Jonathan.
Fantastic. Thank you, Hugo. That was great. I think that picture you note where we're already starting to reach these thresholds of secure operation for SA as an island makes for very sobering sort of technical discussions, especially when you're talking about increasing voltages to perhaps shake off some of these inverters. That's amazing. Fantastic. We're going to get everyone back on the screen, and we're going to head into some Slido questions. So yeah, please continue the questions coming on onto the screen. For those who are just joining us, yeah, you can use the hashtag ESIG-3A. That's ESIG-3A. Fantastic. Well, thanks to all our speakers. Let's jump into the questions straight away. This one goes to Chris to start with. So a combination of solutions needed suggests that all of these will be needed without really considering how much each solution contributes to the operational challenges. From an AEMO perspective, obviously not necessarily just a Chris perspective, but how do you decide the optimal combination, given that there's a risk of overinvestment if all are developed?
Yeah, it's a good question. Thanks, David. And I think this is the big regulatory question, I guess, in this space. And I think as we essentially re-engineer the entire power system to cope with a totally different sort of combination of technologies, how do you do that in the least cost way, and how do you do it in a way that serves the long-term interests of consumers? So I think the important thing when looking at those solution options is really to look at they're not all like for like. They don't all come with the same price tag. Some of them are must-have requirements. So some of the inherent sort of technical standards are low cost, particularly if they're built in at the time of manufacture, and you build in that inherent capability. Other solutions there are sort of market design questions, which that whole market design process needs to work through the pros and cons of the cost of implementing such a change versus the potential value from it. So yeah, I think what I would say is we don't necessarily need everything on that slide altogether at the same magnitude, but we need a combination of those solutions, and I guess for the regulatory bodies here, for the AEMC, the Market Commission, and the Energy Security Board, that's the challenge for them and the rest of us to contribute to is what is that efficient combination.
Yeah, good point. Thanks, Chris, and thanks, David, for the question. I'll throw the next one to Elizabeth. So given Chris's presentation that many of the installs of small-scale DR, do you see any need to reduce these minimum thresholds to capture even smaller DR, perhaps even as low as 1 megawatt, to gain the visibility and the system security requirements?
Yeah, that's absolutely. There is a lot of work currently happening at that regulatory level on how these smaller connected projects can be made visible. And in the immediate time frame, at least the NERs, that little clause, I think it's the 222B1 will allow AEMO to sort of capture that middle tranche of projects, but certainly the less than 1 megawatts are still a grey area from a rules perspective, and that's why there's a lot of current work in the current process, sort of looking at how they can be captured and enable them to sort of be made visible for the purposes that we've seen.
Can
I just add something to that? I mean, it's a really wicked problem, sort of wherever you set that threshold, because however low you go, there's always going to be the question of should you go lower, and at some point you're going to reach a point where it is really not feasible to have that level of visibility. So I think that the bottom-up question is what level of aggregate visibility do you need? What level of sort of aggregate sampling can you use then to scale up from particularly the residential side?
Yeah, absolutely. That is absolutely a perennial question. It really is, and there's no simple solution. That's very clear. Look, we've got a question for Hugo, and then I'm going to throw one to all of you. So Hugo, was the avoidance of SA islanding considered as a benefit in the RIT-T, which is our regulatory investment test here in Australia for the energy or the Project Energy Connect, the interconnector with New South Wales?
So we that has been sort of included in the market modeling for that project. What we find though is for these high impact, low probability events, the economic test, which is a simple multiplication of the risk of that event occurring times the consequence, provides a relatively small economic benefit. But begs the question sort of, is that appropriate? Is that sufficient, taking into account that the risk that the state is facing for that event? But the short answer is yes, and that's included in the evaluation for Energy Connect.
Okay. Well, look, I think it's a bit of a question that follows on from that. And you can almost cue this music, how low can we go? And it's certainly a theme that's come up through these ESIG Down Under presentations. How low do you all think the SA can go, and can it actually go to the zero operational demand?
It can. That
was really confident, Hugo. Well done.
Yeah, I think it comes back to it cannot for an islanded operation. So if you can't balance it that finely, but if you interconnect it and you can manage the credible contingency, then you could say you could go to zero, and that's where energy would come in very handy. That provides a bit of a buffer there. However, then if you get to that point where you get to those low conditions on a single interconnect and you have a non-credible event, then the chances are very, very high that you'll go black.
Yeah, I don't know, Chris or Elizabeth, do you want to chip in there?
Yeah, and as we've pretty much seen, there's a lot of challenges from the voltage perspective. As soon as you start going towards those low levels, currently some of the biggest sort of distribution projects that we look at trying to get them sort of making sure that they've got a good voltage range within that low demand time is when things start to get tricky. So we look at the voltage regulation and all the control schemes to ensure that we can sort of manage that. So I always think of it as when things even get lower, it will become a bit of a bigger challenge from that perspective.
Sure. Going back to the questions, we've got another question in there from David, which I'll jump to in a second, but I might grab Michael's question. Their common theme is visibility and control. What appears to be absolutely stand out is there's no significant DER penetration that can be managed without extensive synchrophasor monitoring, including sequence components, voltage angles, harmonics, including dominant harmonics. Has anyone got any comments on that? Good question, Michael. Thank you.
I might start on that. So we have implemented a pilot project with synchrophasor monitoring across 5 sites in South Australia now. And the intention is to use synchrophasors as the trigger for the upgrade to the system integrity protection scheme. That's all fairly new worldwide. And we have one other installation in the world where that's been done in Iceland. So it's definitely heading that way, that we want to use that technology to capture these events and act quickly enough and take dramatic action to, in a way, keep the lights on in South Australia.
Yeah, I'll build on that. Certainly one of the key findings out of our renewable integration study was the need for more high-speed monitoring across the NEM. It's such a complex system. Even the best models in the world can only model so much. So the best teacher and the best way for us to learn and sort of see what's going on is that sort of synchronized high-speed monitoring across the network. So we've got a project looking at that at the moment. And I know sort of all of the transmission network service providers have got their own projects as well. TAS Networks has rolled out a big synchrophasor network recently.
Yeah, well, that probably leads nicely into perhaps David's question there. Do we have any model for a grid without synchronous generators? If not, how are we prioritising the development of the renewable synchronous generators, e.g. CSP, CST?
I'm happy to have a first go at it. I mean, there's a lot of thinking being done in this question. There's a lot of international collaborations about sort of fully non-synchronous grids, and certainly the views on whether you can operate a grid without any synchronous generators. And I think that the theoretical answer is yes. The practical answer, particularly for us, say in the NEM, is you might want to operate the NEM at times with no synchronous generation, but probably within the same 24-hour cycle, you are going to want to have synchronous generation running. And also remembering that we've got a lot of hydro generation that isn't disappearing anytime soon. So, and still a continuing reliance on gas generation too. So I tend to think about it in terms of how do you create a grid that can sort of migrate during any 24-hour periods from being sort of nearly fully non-synchronous to being potentially fully synchronous. That's the engineering challenge for us.
But maybe adding to that, in the South Australian context, once the 4 synchronous condensers are installed in our state by middle of next year, and once Energy Connect is in, that system is then designed to operate South Australia without synchronous generation. Still a synchronous system because you've got 4 synchronous condensers there. So I think it's depending what you mean by a synchronous system.
Sure. Yeah. Elizabeth, did you want to chip in any on those last 2 questions?
Yeah, there's certainly challenges with trying to make sure we can, even from a modeling perspective, the current cases that are available to sort of get them running through contingencies just from a studies perspective, you get to see some of these real phenomena where the case cannot actually converge under some of those really low synchronous generation scenarios. So even just being able to do the power system studies that support some of these projects are way challenging when you're trying to sort of look at that from a minimum perspective. So it also begs the question on how we sort of are able to sort of do some of this modeling upfront, taking into account the challenges in conversion of some of these models that we see.
Yeah, thanks, Elizabeth. Really good points. I'm just going to throw one. I'll maybe start with Elizabeth again. Just there's a couple of questions related to this in terms of the command and control, centralized monitoring, centralized data management versus decentralized. And we heard Tesla last week talk about, even in their VPPs, they're running an almost autonomous model rather than a centralized command and control. Where do you think the common ground is? And this goes to all three speakers. Where's the common ground on controlling it from a centralized point of view to, almost allowing it to, do what it needs to do with some monitoring coming back up? Where's the common ground? Maybe, I don't know, Elizabeth, do you want to have monitoring and control, the common ground?
Yeah, and I think Chris's point where you're going, is there going to be a limit towards how much you can see from each individual? So maybe we're looking at it from that top-down approach where it's how much can we collectively see? Because I guess if from the perspective of the example where I gave, you got a few little projects connecting onto the same area, so you're increasing congestion. But at that particular point, AMO may not be able to sort of have the discretion to reclassify this generator as unscheduled because by then the congestion isn't there yet. So then that project may connect under 20 megawatts or under 5 megawatts. And then maybe in the next 3 or 4 months, these other projects then come around and then that becomes a congestion risk. So then you're kind of looking at it from the perspective of collectively, how do we then get as much of this seen? Because from an individual level, the timing might mean some of these projects don't actually get into that process, even though they were seeing sort of congestion coming through that process. So probably I liked Chris's idea of the top-down approach rather than trying to get as much into each individual one, given the circumstances and the timing.
Sure. I mean, Chris, did you want to follow through with that?
I mean, I think the other consideration is how fast do those control systems need to act. That's the big question here. If we want to push the system to be if we choose to push the system to be a really low inertia system where everything's moving really quickly, then you've got less time for your control systems to make their decisions. And to Elizabeth's comments earlier about sort of voltage control and hunting between different plants, the same goes for whatever the control system is, if it's frequency or voltage control. So I think if things are moving slowly, then you can do a lot with sort of AI, machine learning and autonomous controls. And we see that from the distributed solar fleet in their sort of internalized response to frequency. We get some really good responses in that regard. The extent to which you can run an entire system totally autonomously, it's a really good question. And yeah, I think the proof will evolve over time.
Yeah, definitely going to start seeing it in South Australia. I don't know, Hugo, did you want to have a crack at that?
Yeah, maybe sort of at the very high level, I'd say there's two thoughts come up in my mind. The one is improve the standards or lift the standards that the rooftop PV from a resilient are more resilient to system shocks. But then it might be something that what is that? Should most rooftop PV or any DER really be part of a VPP, and that VPP then body is interaction with the AMO operations that you can have sort of fingers into the distributed systems to be able to dispatch them effectively.
Good point. That's a good point. While you've got the microphone there, Hugo, Carl's come up, got a question there, which is great. It sounds like SA needs to procure more FFR to protect against these mass disconnections.
So that's happening.
And how?
Yeah, it's happening right now. So AEMA has declared a shortfall, which the suggestion is that we meet that with contracting for FFR. And we're in the process of sort of starting to set that up and to go to the market in the next month or so. Effectively, that means is that will be added to the transmission use of system charges. So will be basically customers at large will be paying for that.
Right. Thank you, Hugo. Thanks, Carl, too, for the question. There's a question that came in fairly early on in the piece, AEMO, and it was directed to Chris, and that was, is AEMO considering updating PV forecasts from customer uptake during COVID? Does that increase the urgency of the proposed actions? Yeah,
really good question. So, I mean, people might have noted in the dagger plot that I showed that some of the projections for 2025 didn't look that much higher than 2019, and that was based on our ISP modelling, We've since released our electricity statement of opportunities, which has got a much more aggressive sort of projection for PV uptake, and we're about to start consultation now on the next round of our integrated system plan. And definitely this question is front and centre in our thinking, is kind of how aggressive do we need to look at those forecasts. We know sort of the on-ground results seem to be that people are, there hasn't been a slowdown in PV uptake. If anything, it's increased during COVID. So that plus changes and projections in demand as a result of COVID are definitely a big focus going forwards. Does it increase the urgency of the proposed actions? Yes. Look, if things are going faster, then we need the solutions in place sooner. And I mean, as Hugo showed, the South Australian case is really quite critical. So those actions are already urgent, and the question is sort of how fast do we need to move to get ready for the other states? And there's quite a few things already in train there.
Sure, and I think Victoria and Queensland are also creeping up the curve pretty quickly. I understand. Look, as we're talking about forecasting, obviously forecasting pricing leads to how we hear people talking about pricing signals for some of this DER coming on, coming off, loading on, loading off, etc. And where when we talk about AI and so forth, and here in the Australian market, we obviously have a 5-minute energy market, and we have 5-minute FCAS prices. So I mean, we're already down at very, very finite levels of price estimation and forecasting. What sort of other pricing signals, though, do you think we need as we sort of move into the next couple of years? I'm happy to throw it to anyone who wants to take a crack at that one.
Yeah, I mean, I can have an initial go. It's not my core area of expertise, but I mean, I think we're thinking there in terms of both sort of static network tariffs and the signals that you're giving for how people consume electricity and how they generate their electricity at home, and also how that relates to feed-in tariffs for solar and the signals about sort of when you want that exported to the grid. Then at a sort of a broader market perspective, it's the sort of two-sided market considerations that the Energy Security Board and the AMC are considering at the moment. So signals that actually allow greater participation from flexible load to bid into the market and help sort of move itself around in response to periods where you've got excess generation.
Sure. You go, Elizabeth. Did you have any views on the price signalling?
From I think that's at the distribution level. My view is that price signaling probably doesn't have that much of an effect of people's actions of investing in these devices. I think that's given that something like your rooftop PV is really of benefit 98% of the year. It's really those middle of the day weekend scenarios, low demand, where they cause us as NSPs and EMO big issues. It would be hard to come up with a pricing signal at the household level that would change that. I think it's more an effect of what are the actions, and these are actions being taken in South Australia already, that any future rooftop PV will need to be controllable. That in those severe conditions doesn't happen much, but if we have those extreme low demand conditions, that they are part of a system that can be switched off, basically. So the messaging that is challenging is that seems unfair to other people that have system on their roofs, but that's the situation we're in. We just need to manage the messaging correctly.
The other thing is, how do you incentivize new loads there as well? So people that think about sector coupling and how we shift other things into the electricity sector. So particularly if you think about electric vehicles, huge potential new load that is, if done right, quite flexible. How do you incentivize that into the middle of the day so that you start to sort of counteract the minimum demand problem that Hugo was showing?
Dead right, and there's certainly going to be a lot more discussion about those types of things as we go forward over the next few weeks, months, years. This is absolutely going to be one of the key issues going forward. We've actually come to the end of our allotted time, and I think there's a number of questions we haven't got to. We'll try and get to some of those through the speakers over that next period of time. So, but I'll just want to thank our speakers for giving up their time, giving up their time early on Australian mornings, but also to all their visitors who have come and visited, and those who watch it after the event. Fantastic to have you here with us talking about these technical issues. You'll be able to download the video within a day or two, which is great, and use that for your benefits. But I think that's all from me. Thanks again for joining us. Thanks again to our speakers, and thanks to AEMO and ESIG for arranging this ESIG Down Under, a really valuable contribution to what's going on in our very, very quickly changing electricity grid. Thanks, everyone.
Thanks, Jonathan.
Thanks, Jonathan. Thanks, everybody.
Thanks all.
And
Thank you.